All right, seems like we're live. Just double check. Yep. So we're going to be starting in a couple of minutes, but in the meantime, tell us where you're from, where you're joining us, and what brought you here, probably Dask. And yeah, I will introduce myself properly as soon as we start. But for now, the early joiners, I'm Nati Clementi, a software engineer, open source software engineer at Coiled, and we're going to be learning some Dask today. So let us know where you're joining from, and feel free to ask any questions for now. We might probably drop the link soon of the content in case you haven't received the email. So we're going to put it in here. And if you want to follow along, then you can go into that link and there should be a binder button. And then we're going to start from there. So yeah, in the chat, we also have like Christiana from the Coil team, as well as Ian, another software engineer at Coil that will be taking a couple of questions on the chat. As I probably, when I'm working, I'm not going to see them properly, but yeah. Oh, we have people from Germany. Nice. It's probably a little late over there, but great. Right, let's give a couple. Probably start in 3 minutes. That sounds good. I think someone says from Arlington, Virginia. I think I know that one. That's probably Abhilash, ex-colleague. Then yeah, cool. So if you haven't clicked on the link that has the repo on the binder button, if you have not installed things locally, you can follow along by clicking on the binder button that is on the repository that we just linked. It will take a couple of minutes on the spin up, so make sure that you have that ready to go. But yeah, we'll start in 2 minutes. Meantime, I can tell you a little bit about myself. So I am originally from Argentina, so therefore my accent. So pardon if there are a couple of words that are mispronounced. And I've been working for Coil for a good amount of months now on an open source team, along with Ian and other people. And yep, this is like our first Dask live tutorial. So any feedback that you can give us on how can we improve and then how things can go better, then that will be great. So I'll just give it 1 more minute and then I'll share my screen and then we give it a go. Well, I'm going to share my screen now, so then we'll see if you can all see the font well. So share. Let's see, it's going to take 2 seconds. And all right, so yeah, So you should all be seeing like a Jupyter Lab. If you haven't launched Jupyter Lab in your laptop, if you are running things locally, you can launch Jupyter Lab on the repository. If you are on Binder, you should be able to see something similar like this. Just it will be on Binder. So for now, let's just get started. So if you're on Binder or in your local machine, you can go to the notebooks, and then we have a series of notebooks that we are going to go over today. And the first one, it's a little bit of an overview. So let's just begin. All right. So you're probably here because you're interested in Dask, but you might wonder what is Dask and when to use it. And if you hear of Dask or you ever have heard of this, then you probably have these questions. It's like, what is it and when do I use it? And before I try to give you an overview, I just want to tell that there are amazing resources about Dask, like the Dask documentation, and then you can check the GitHub repository, and you can also engage with the community in the Dask Slack. All these links are on the material, and then feel free to just go to reach out to the community if you have problems with Dask. Slack is a good place. The documentation is very, very good. So then you probably will find your answer there. But for now, let's try to have a small summary on what is Dask, and then how can we get to know Dask better. Just to check, is the screen fonts big enough? Are you all able to read what I read, or is too small? I can always make it bigger. Let me know, just in case. I probably can increase the font a little bit. But if you can see well, I'm just going to go ahead. So Dask is a flexible library for parallel computing in Python. And the good thing about this is it follows all the PyData ecosystem. So if you're familiar with NumPy and pandas or Scikit-Learn, then Dask is going to be very familiar to you. And you can think of it as a kind of like their faster cousin or someone like that in the family. So then things that look in pandas, for example, like a read CSV, and you will say import pandas as PD, and then read CSV, and then we can perform a group by. So on the left, you will see this. Then on Dask, this will look very, very similar. So we will do import Dask DataFrame as DD, and then do a read CSV. Similarly, you might notice there are some asterisks here. We're going to go over that, but just so you get familiarized and how similar these computations are. So since they're all family, Dask allows you to scale pretty much any workflow with a small amount of change of code. Like the fact that you already have some code, probably you'll have to tweak small stuff, and then suddenly you'll be able to run things in parallel. So it works in your laptop, but it also scales to large clusters and then you could have some diagnostics via dashboard. We're going to explore a little bit of all of these ones as we go. But on a general level, we count with collections, which are called Dask arrays, Dask DataFrame, Dask Bag, Dask Delay, and features. We're going to go over some of these, not all of them. And these collections create a task graph, which the scheduler, and we'll go over to what the scheduler is in a minute. The scheduler executes these task graphs. And there are different kinds of schedulers, and we're also going to talk a little bit about that. But overall, we will have a task graph, and the scheduler is going to execute this task graph. So a little bit of jargon here. We actually have a couple of words that you will hear all along every time that we talk about Dask. So they are client, scheduler, and workers. So the client is the user-facing entry point for the cluster users. So usually this is where the Python code lives. The client is where the Python code lives. And it communicates to the scheduler to pass the task to be executed. The scheduler you can think of as the task manager, and it sends tasks to the workers. And the workers, as you might think, it just computes the work. It's the ones that like are going to take care of the work. So I guess one of the best questions that we have is, when do we use Dask, and when it's suitable, if it's suitable for you or not, and when you will be using it. So there are a couple of questions that you might want to answer when you're like seeing this. So one of them is, you not always want to use Dask, and if you can't avoid it, then you might want to avoid it. And why I say this, let's say that you can ask yourself a couple of questions like, does your data fit in memory, in RAM? If your data fits in memory, then pandas and NumPy are great libraries, and they're pretty well optimized. So you want to live on the pandas and NumPy as well. And Dask might be able to do something, but we strictly recommend that if things fit in RAM, you just use pandas and NumPy. If they don't fit in RAM, then there is a good chance that Dask can help. Does your competition takes forever? Well, if they do take forever, then there is a chance that we can actually help you with Dask. If your competitions don't take forever, awesome. You're very lucky. And overall, we can say that if we think of the dimensions of a scale, like this plot, you have pretty much what is called a compute bound kind of problem, a memory bound problem, and then things that fit in RAM. So if you're on the bottom left corner and things can live in RAM, they fit in RAM, and they don't take too long to compute, then just don't use Dask. Anywhere else, like if things take long to compute, like a grid search or random forest, then you might want to use Dask. And if then things don't fit in memory, you definitely want to consider to use Dask. So now there are a couple of disclaimers that we want to go over, and before we start actually getting into the code. Is when we say Dask might be able to help you, it's because first you should try to accelerate all your code with NumPy and Numba and see how pandas perform. But once you're considering Dask, there are a lot of specifics about your particular problem. And it doesn't necessarily mean that because you just use Dask, things will run immediately faster. There is always some work around that. So ideally, after this tutorial, you will have a better idea on when you can use Dask, why you should use it or not, and see if this applies to you. As I say, Dask documentation is impressive, and there are a lot of good best practices written down. So I would encourage you, if you want to dig deeper on if you should be using it or not and how to use it, always check this best practices that are linked on the material. And there is also great material and great readings about why you should use Dask if you're already not convinced. But I would say if you are living on the Python ecosystem, then you should probably be using Dask if you need it. And now let's try to learn a little bit more about this. So a lot of chatting. This was a big overview about what Dask is, but let's get to some coding. So now we're going to go to the first coding notebook, which is the Dask Delayed notebook. And most of these materials, it's based on material that already exists on the Dask tutorial, and then some other talks and tutorials that have all my colleagues at Coiled have given. So you will find some version of this material all over the internet. Feel free to go and explore all those materials too. They are like far more extended, and then you will get something out of them. But for now, let's start talking about Dask Delayed. So sometimes we have problems that are parallelizable, and you might want to see how to parallelize those problems and be able to use pretty much your existing code by applying some sort of function that makes your things go faster. So that the perfect candidate to do that will be Dask Delayed. So if we can identify if there is some level of parallelism and you can identify, we can hopefully exploit that parallelism using Dask Delayed. So let's just simplify things. And then let's just simplify things here and try to understand how this works with two simple functions. So to start, we'll see here two functions that they simulate some kind of work. So we'll have an increment function, which will grab a number and increment this number by 1. And we have a sleep, which is like a 1 second delayed over there to simulate more of the work. So if we run this cell, nothing happened, just have our functions there. So far, everything is serial. And if we time this, we will see that this takes approximately 3 seconds. So let's just run it. And then the reason why I say this will take 3 seconds, it's because we have 2 calls of inc, which is 2 seconds of the sleep, and then the add have another second. And the other computations that happen are super fast. So then we probably won't see that much of a change. But now these computations can be seen or represented with the following graph. So if we see that the call to inc1 and the call to inc2 they're not depending on each other. So if we have 2 different machines that they can run them in parallel, then they will run in parallel. And then once we get the result, see, the results will be this square boxes, then we will pass this to add and then get the result. So let's see if we can use Dask Delay to actually make things run in parallel. So Dask Delay works on the way of a decorator, meaning that we're going to decorate our function, and then that will hopefully take care of things and make things run faster. So we import delay from Dask. So from Dask import delay. And now the way that we decorate these functions are by basically wrapping the function or passing the function to the delay decorator. And then we give the argument that we pass to the inc function in this case, or the function that we just decorated. So this is exactly the same workflow that we had before, but now with the delayed objects, wrapping around the functions. So if we run this, let's see what happened. Okay, so you might notice that now we got a wall time that is of the order of microseconds. This is like super fast, but so far we haven't done any computation yet. When we call delay, the delay version of the functions and passing the argument, the original function is not called yet, right? So let's explore this object and see what we get. So we have here, as you see, if we print C, this is a delayed object that had this add. So this add refers to the name of the function that we have here, but nothing has been computed yet. I didn't get the result. So let's try to see how this object looks like, and hopefully we will understand a little bit more. So if we do see visualize, we'll see here something that looks like the interpretation of the graph that we had before. So C now is this version, this task graph that tell us how the tasks are going to be executed. So at this point, the object C holds all the information we need to compute the result, but we still need to compute it. So the way that we compute the result is by calling compute. So let's see how long this takes. So if we run this and we time it, you will see that now it takes 2 seconds, meaning that the 2 inks are running in parallel and taking 1 second. And then we have another second from the add. So yeah, we make things faster. Now, if you are following along and you are running things on Binder, you might have not seen this speed up of 1 second. And the reason for that is because on Binder, like we have limited resources. And by default, we are assigned one instance that has 1 core with 1 thread. So there's not that much to do parallel. For now, if you're running and following along on Binder, you could do this workaround And we will actually explain a little bit later why this works and then give us a little bit of more of a speed up. So you can do this import, and it says, so there is dot on C visualize. So someone has a question. It says getting error 2, no such file or directory dot on C visualize. I'm not quite sure what's happening there. Maybe Ian can help a little bit on the chat, but it might be something is happening in there. Oh well, we'll follow up. We'll keep following. Let's see how can we use this to parallelize a for loop, which will be a typical example of something that is embarrassingly parallel. So we have some data here. So let's say if we look a little bit at this, we look a little bit at this, then we have a list that goes from 0 to 7. So we have 8 elements. And then when we try to parallelize a for loop, let's see how this looks like. So we have a sequential code here, where what we are doing basically is applying the increment function to every element of our data, appending that to a result list, and then we're summing on this element. So we have 8 elements. I would expect this to take 8 seconds. So let's try there we go. We got 8 seconds. So now we can print the total. So now we have this. So far, nothing is parallel here. But let's see if we can parallelize this. So this could be an exercise. I am going to do it with yourself. You have the solution there. But as you might notice here, I left you some hints. So how can we do this more parallel? So we can go over here and then apply the delay function, delay. And then we got to do it over here too. So then we wait for the things and then sum them. So if we run this code again, instead of taking 8 seconds, this should take ideally faster. If you're in Binder again, this might behave differently. If you did add on a cell the code up here, then you should be able to see some level of parallelism. So let's see what happened on my machine. So here is the solution. So as you said, we wrap now ink into a delay, and let's compute this. So right now, as we mentioned, we're not seeing things. And when we do total, and we have here the sum object. So then the sum will be part of the whole task graph. Otherwise, if we don't do a sum here, then the sum will be trying to compute things as it goes, and then it might not work out. So if we visualize now, we'll see a task graph that has the 8 ink calls. Ideally, this will run in parallel. And then once these guys are done, we send them, we get the sum, and then we'll get a result. So let's try to compute this. So if we run this, we'll compute. And voila, we see 1 second instead of 8. So this tells me a little bit also something about what I have on my machine, right? Like on the back, when we use delay without having a distributed scheduler, we'll see what a distributed scheduler is later, but we are relying on a single machine scheduler. And thus we'll use what is called the thread pool executor, which by default use all the resources available on my machine. So I will be able to sort of guess that this simple computation, if it runs in 1 second and I had 8 computations to do, probably I have around 8 threads available. So one way of checking this, or how many resources you have available on your machine, you can check what is the CPU count. So if I do import OS and then I run what's the CPU count, I see 8. So then this tells me that I'm using all this, I'm using all these resources, right? So if you are in Binder, probably this count might look higher than what you have, but then things might not run necessarily all in parallel, especially if you set the config option that I mentioned before to 4. So you will have 4, but then 4 threads, but you might have more CPU counts. So we will explore a little bit more about the things, but for now, let's see another way that we can use the delay object. So if you already have a function that it's embarrassingly parallel or a simple function, then another way that you can do is decorate this function with this nice syntax. And that function will immediately be a delay function. So let's see what I mean about that. So we use a delay, nothing happens. Now, if I try to see what happened here, I will see the D now, which is the call to the function. It's already a delayed object, right? So as an exercise, try to do or convert the other functions that we had before, the inc and the add function, to something that looks like this. That should take 1 or 2 seconds copy and paste, but I'm going to be like revealing a little bit how would this look like. So that's how the inc function will look like. And then we have another one. Okay, I just caught one question that I think is a really interesting question is, what if the list has more elements than the number of cores? So it will be using the cores as they free up, right? Yeah, I see Ian is taking care of the questions like a champ. So thank you, Ian. It's hard to follow with the questions, but at the end we will have some time for questions if you have any remaining questions, and hopefully we'll grab all your questions, the common questions, and then probably try to make something out of that. I could modify the material and then improve from there. So thank you for keep asking questions. All right, so coming back to this, so we have now that our inc and add functions are parallel functions, let's put it that way, or delayed functions. So let's see if we can do some operations with these functions. So the delays object supports several Python standard operations. So we can sum 2 different delayed functions, and then we can multiply things and see how this behaves. So one simple example is, let's just do multiply 2 calls of inc and add them to 2 other different ones. And let's see how this graph looks like. So over here, we can just visualize this. And I probably didn't, I didn't run this cell. So that's the problem we're having. But there we go. So you see here, we have 4 calls of inc. They will get their results. But then now this multiplication and add are the built-in functions, multiplication and add. So they're going to pass this, the results of inc, going as inputs of the multiplication, and then the results of those goes as inputs of add, and then we'll get the final result. So if we compute this, let's see how long it takes. So this took 1 second. And the reason why this is taking 1 second is as 1:01. So the 1 second, we will guess that it comes, well, guess now, it actually comes from running the 4 incs in parallel. And the remaining time is the remaining computations of the multiplication and the sum that are happening here. In this case, this add function is not the same add function that we had before. This add function doesn't have a sleep of 1 second. This add function represents the plus that we have over here. So another example, or how can we get things a little bit more complicated, is using these functions now on a similar for loop example that we had before. So before we have this data of 8 elements, and we were performing some operations, appending it to the output, and then summing the things together. So now, these calls of inc, double, and add are the parallel versions that we just created up here when we decorate them with the delay object. So if we run this should generate an object that also have this sort of like combination of inc, doubles, and add, and it should look a little bit bigger than the things that we were doing before. So let's try to visualize this. Here we go. So what do we see here is we see the code, we have an inc call and a double call per element on our data. So we should have 8 doubles and 8 inks on here. So if you count, you'll see that. Then once they get the output, they pass that to the add, and the add to the end to the sum. So now let's time this. And we should get things faster than 8 seconds, right? So yeah, we get 4 seconds. So that's great. So you learn your first steps into parallelizing things. There are way more resources about Dask Delay, and this is a really well-known tool that it's used in multiple different scenarios. Things can get as complicated as you want. I would highly recommend going over some of these resources, but for now, we're going to stop here with Delayed, and we're going to move to the next lesson that touch a little bit more on the difference between the schedulers and the different schedulers that we have available. So let's just go over that then. So as we mentioned earlier, on the first intro or sort of overview notebook, we have multiple or different kind of schedulers. To start, let's just recap on what this scheduler thing is. So far, we've seen only the power of Dask Delay. We got familiarized with the idea of task graph, and we sort of get the computation. But what does it mean to be executed, to these computations to happen? Who takes care of this? Well, this is the job of the task scheduler. The task scheduler is the one that will send the computations to the workers, or the task to the workers to be computed, and then collect those things, and then get our results. So we have, on overall, in the grand scheme or at a high level of things, we have a single machine schedulers, which is like single machine. Things live in Python. It doesn't require any setup. It will be used in the Python standard library, and it provides basic features on local processes or thread pools. And these words are could be a little bit complicated. I would recommend going, if you're interested in knowing a lot about the differences, you can actually read more on documentation. But on the high level, so threads, when we use threads, the thread scheduler execute computations with the thread pool executor. And the thread scheduler is the default for Dask array, Dask DataFrames, and Dask Delay. Processes will use the multi-process scheduler, execute computation with process pool executor. And this will be the scheduler by default for Dask bags. In this tutorial, we are not going to cover Dask bags, as it's a little bit of a more advanced topic. But if you're interested in knowing what Dask bags are and how you can use them, there's plenty of material on the main Dask tutorial, as well as like the documentation. And the single-threaded scheduler, and you might wonder, why do I want to run single-threaded things if we're trying to make things parallel? Well, this scheduler can be very useful when you're trying to debug. Debugging things in parallel is a little bit complicated, so you can set up the scheduler to be single-threaded to be able to debug and then go back to the parallel versions. So let's see a little bit of the schedulers in action and then how things change when we run with one or the other. So all-time inc function, we've just been getting very familiarized with this function. We had same function before, we increment by 1, we have a delay. So if we see this function here, if we do the for loop that we had before, it should take now 1 second, right? Remember, in my machine, I have 8 cores, so then this 8 threads will be doing perfectly this job in 1 second. Now, what happened if I set the numbers of workers to be smaller? So currently, we're still using threads, and this will be, if we set the number of workers smaller, this should take a little bit longer. So let's set the number of workers to 4. So I will be using 4 of all of my resources. And when we do the compute, this takes 2 seconds, as we expected. We have now 8 tasks that we want to run, 8 calls to inc, and I have only 4 workers available. So we'll do 4 in 1 second and then 4 in the next second. Now, we use the multi-process scheduler. This is not ideal for this case. Like, you will see that there is some speed up, but it's not what it's recommended to use when we have delay objects. But just so you see that there is an option, and then this will run on around 6 seconds, I believe, or so, because we will run this before. So this would tell me like, hey, I have this 8 cores that I'm using, but then if I run with processes, things don't seem to be that fast. So then probably this is not the right scheduler for you. Now, with a single thread scheduler, I would expect this to take 8 seconds or approximately that. So if we run it, we will see that things are running in, they're not running in parallel. So then they should run one by one. So it's going in a for loop the same way, old-fashioned way, the whole serial way. So we've been talking a little bit, and we mentioned about this distributed scheduler. And then, like, what is a distributed scheduler? Well, despite having the word distributed on its name, it also works on a single machine, like your laptop. And there's a reason why we usually recommend this scheduler, and it's because it offers more features and diagnostics. And you can think of this as more of an advanced scheduler. The distributed scheduler can be used, like, can run in a cluster, can run locally. You can deploy clusters, but this involves a little bit of a bigger setup. And there is plenty of documentations of how you can deploy your own clusters. But alternative, you can use certain tools like certain softwares like Coiled, which actually will do and take care of everything for you. And if you're interested in trying things like this and using a Coiled cluster, you can start for free. And we will see towards the end a little bit how you can get set up and then use some of the free credit for this. But ideally, you could run on a cluster very simply using tools like Coiled. So for now, let's just set up a cluster, a client and a cluster locally. And then let's see how all this stuff look like. And especially the dashboard. We strongly recommend people using the dashboard to get an idea on what's happening. So if you are on Jupyter Lab, so first we need to start a client, which will start a local cluster. So I am going to be asking for 4 workers now. We know that I had 8 cores on my machine. Let's see what happens when we do this. So the first thing you'll notice is we have a link here to a dashboard. So if you click on this link, so I'm going to click on this link, it just opens a separate page that it looks like this. So this is the dashboard. Now, if you are on Jupyter Lab, there is a gray Dask extension that you will see on the left here. So I'm going to click on this Dask extension, and I'm going to sort of recreate the dashboard that I have on one page. But there are plenty of other plots that you can check while you're running your computations. So I'm going to get the task stream. So we actually can put it in there. I'm going to get the progress. We'll see what these things are on a second. I want to see what's happening with the worker's memory. So ideally we'll have something like that. And we can see also what's happening with the cluster memory. So we do that. And you can drag and drop these ones. I'm trying to see if I can, oops. Well, this doesn't want to. Let's see if we can get it more, well, more set up in a way. Something like this. Actually taking some time. Haven't used this in a while, but let's do something like this. So we will see things happening on this dashboard as we go. So let's try to do some computations. So the computations that we did before, let's just run this compute. And now by default, we're going to be using this cluster that we created with the client that we just generated here. So if we do total compute now, we will see things happening in here. The progress, we won't see here the progress right now because this task already computed. But what you have on the right here on this dashboard is you have one line per thread. So if we inspect a little bit our cluster with the information over here, you see I have 4 workers and total threads 8. So if I go down and I click on the scheduler, I see all the information, have 18 gigs of memory, and I can explore every worker. So I see that I have 2 threads per worker. So we have 1 worker, there are 2 threads, and so on and so forth. We see on the memory plot, so far, this doesn't consume that many memory, but we'll see each of these lines correspond to 1 worker. And the cluster memory is like the accumulation of all the memory used over here. This memory plot has a lot of information. As we do more computation and more advanced computations, you will see different colors happening in here, different transparencies. We're not going to go into the details of what that does. There's great documentation and there are nice blog posts about what managed and unmanaged memory means. It's a little bit advanced, so we're going to leave that for now, but let's carry on. So another cool thing that it has, the scheduler, the distributed scheduler, is that we can actually use the futures interface. And this is another Dask collection that implements a superset of Python's concurrent futures. So it's an interface that provides like a finer control and asynchronous computation. So you can do nice things with this. If we go back to our inc function, serial function, let's see how can we use this futures interface to do some computations. So inc function, we call it, just give us 2 serial version. We can submit this to the cluster by actually telling the client to submit the inc function with an argument 1. So if we do this, we'll create this future. You see here, there is an inc that has happened there. This plot is not showing nice, but let's see. Here you will have, these are all the tasks, just 1 that are of this type. So we just only submitted it once. There's not much thing to do. Now, if you see here, it says inc status pending. We have this thing here. Now, when we do the client submit, the function, the client submit function sends a function and an argument to the scheduler for processing, and it returns the future. So we'll see eventually now, like when we run again, this will set future finish. But so far, we don't have any result or anything. If we want the result, we got to call dot result, and then we'll get the value. So if we do this, we get 2. So great. we just got a result and we submitted something to the cluster, get it. Now, if we want to submit more than one thing, like what we're doing in the for loop before, we can actually map all these operations. So the way that we do this is we use client map, and then we pass the data that we want as an array or in a list, for example, in this case, and this will create a future for each in call on the cluster. So if we run this, we see all this pendings. This one, it says finish, and this is the one that corresponds to 1 because it already had it. It's like, okay. And then we see all the other ones that says pending. And if I run this again, if I check what futures are now, futures, they all should say finish. And as you notice, like here in the dashboard, all of these tasks have the same color, and these are individual tasks. So on the task frames, every rectangle corresponds to an individual task. And on the progress, this is 8 out of 8, but it's the accumulation of all the tasks. So these are by task type. So by task type, I'm sorry. Now we want to gather the results. What we'll do is just run client gather, and then we can get the results back. So we can delete the futures. You can actually remove a future by deleting it, and you can check that the length will be 7. So as an exercise, you can try to parallelize this for loop by using client submit. So you can get these functions that were over here. You can parallelize this code. So we have this are the common functions. They're not serialized. And then if you want to try, you can parallelize this code over here. So ideally, we will be doing something over here and over here to actually see what will happen. It's similar to what we did with delay, sort of, but now we're just submitting this to the client. So the solution is over here. So nothing too impressive, but we'll do client submit, and we pass the inc function, the double, the add, and then we'll see what we get. So we do this, and then we call result. We should be seeing something happen on the dashboard. Yay, we see a bunch of things over here. Task completed and things being in there. So to go a little bit over what's happening in the dashboard. So as you see now, we have add here. So all the tasks that are here add, they have the same color. So these are individual tasks. And then we have some, which is a different one. It's over right there at the end, super tiny. And you see that there are different colors, some shaded, some sort of transparency, and some things that are still darker. We will go over what these colors mean a little bit later in a better example. But for now, you can just think of these are the staggers, that the tasks that are completed. This like 10 out of 10, 18 out of 18. And then the task stream show us like individual tasks. So as a good practice, we will close the client for now, because when we move to the next lesson, we're going to be seeing something slightly different on the dashboard. So we want to just close this client and we will start a new one. So far, this is more on the scheduler, but we'll keep the task streams and the things going on. But you will see that when I close it now, things will clear out. So now we've seen a lot about delay. We see things about the schedulers, but what about what I told you earlier, that if you have data frames on pandas, you can actually move to use Dask DataFrames, and the syntax should be very similar. So then we'll see the things. So I see a question that says, do you get the dashboard only if you are on Binder? No, you get a dashboard if you are on your local machine. You should have gotten a link when we started the client. So that link will open a local host. So you can have it there as a dashboard, or you can actually, if you launch Jupyter Lab, you should have like have this Dask extension on the left. Now it says dashboard not connected, but I'll show you like next time, like on here, you can select multiple plots and then get that. So coming back to data frames. So as we learned on Dask Delayed, we can parallelize functions using Dask Delayed. But luckily for us, we have multiple Dask collections that already include parallel versions of multiple functions. So someone already took care, someone actually, all the Dask contributors and maintainers took the job of basically creating the parallel versions of multiple pandas functions, and so then we can use it with an easy interface. So the Dask DataFrame data model, basically what we have here is, for most of the part, the Dask DataFrame feels like a pandas data frame. However, like internally, what we have is like multiple tiny or tinier pandas data frames. So you can think of a Dask data frame as this big thing, and then each of these chunks or each of these partitions is a pandas data frame. And then there are plenty of operations from the pandas API that are supported on the Dask part. And you will see how we can do similar operations like group bys and summing things and grabbing things from columns from the same way that we do on pandas. So there is a good amount of lists. There is a list of some of the operations we can do in the notebook, but let's just see some things in action. And one thing to keep in mind is, when do we want to use Dask data frames? So if things are working good for you in pandas and you're not having memory errors and things run okay, there is no need to go to Dask. So if things don't fit in memory, then Dask is it could be a good friend. So if you're having this memory error, then you will want to use Dask. Now, during this tutorial, we will be using some data that is not super big, and it probably still fits in memory. It actually fits in memory, just to showcase things, and then we can run things and display it easily. But in general, like you can see on other Dask tutorials, and you can see also certain workflows, and there are plenty of videos on YouTube where you can actually see a better showcase of this stuff. So we can load some data. So if you run this, if you are on Binder, when you run this, it will create a smaller data set than the one that you will see on me running here, but hopefully will allow you to run this stuff. So you just create the data. This will like get it on a directory for you. If you're in Binder, this will get on Binder. For me, it will do it locally. So now we just have this pass. And remember at the beginning that I told you that we'll explore a little bit what these asterisks are. So if you just explore a little bit the data that we just downloaded. So if we go back to the data folder, initially there was nothing there. You will see now a folder that says New York City flights. And you'll see that we have 10 CSV files. When we are loading the files here, or when we're reading them, this thing that we call files, we're reading them all at the same time. So we're reading all these files into a Dask data frame. And each of these files will be like a pandas data frame, right? So that's a good perk. If you wanted to do this on pandas, you will have to do a for loop, which you don't want to do that. So now we import, as we mentioned before, Dask data frame as DT, and then let's just read this data and take a look at it. So, oops, I then import Dask. All right, so here, just make this smaller. So far, if I want to explore what's inside data-wise of the Dask data frame, I don't have things here. I see ... I only see the columns, names, the data types. I see the number of partitions, which because we had 10 files, then in this case, we're seeing 10 partitions. There are ways of repartitioning this. That's a little bit of a more advanced topic where you can find all that information on the documentation. But you can notice here that we have sort of a representation. So let's explore columns, something that you will do when you're with your pandas data frame. If you just have a good amount of columns and you just want lists, and you don't want to read them all by scrolling, you could just type columns. So far, things are nice. Data types, we can check them. We can see also that Dask DataFrames have an end partitions attribute. And this is a little different from pandas. In pandas, you won't have partitions. So this will tell us how many pandas data frame make up the Dask data frame. So we had 10 files, and because the way we read it, we can see here that we have 10 partitions. So if we want to visualize this, we can see that right now, what we have is 10 different read CSVs. And so far, we haven't done anything with the data. We haven't done a compute. So that's why we are not seeing many things happening. Also, so far, I haven't started a client. So what we're using on the back is a single machine scheduler that we have for using the thread pool. So if we want to, take a look at the first, like the operation head, like you want to take a look at the first couple of rows. So this will actually trigger a computation, and that will retrieve probably the first couple of things. So let's see right now. Yeah, we can see the date, and the day of the week, and a couple of data right now. So let's try to actually do some operations that we would normally do in in pandas, and let's see what happened. If we want to see what's happening in the dashboard, we need to create a client. So we usually recommend it. So far, we haven't created it, and we did some small operations. But from now on, if we create a client, we will see now for the person that was asking before, like now that we created a client, we have this dashboard here. There is a link. So if you click there, you will go to the status page. But if you are in Jupyter Lab, not Jupyter Notebook, in Jupyter Lab, you have this Dask extension. And then now all these are lighting up, and you can choose multiple plots that you can see, and you can take a look. For now, we're going to stick just to this 4 plots, but there's plenty of information that you can get from there. So if you want to do multiple operations on different pandas data frames and on different files, as we said, the way that we will go about this is by reading all these files on a for loop and then performing the operation, appending it, and then getting a result. So for example, let's imagine that we want to compute the maximum of the departure delays, right? So we have, if we were on pandas, then we will probably create a list that will append all these maximums, and then we want to just see which one is the maximum out of all of them. So we don't want to deal with for loops. So let's see how that looks like on a Dask data frame. So if we just run this, so on the data frame, we grab the column, same way that you do it with a pandas data frame, and then let's just check the max. So far, similar with the delay object, we haven't done any computation yet. So we got this Dask data frame scalar series kind of object. So let's see how this looks like with Visualize. So far we have the task graph on how the computation will look like. So we have here, this is a little bit tiny, but you might see that what we get here are a bunch of read CSVs. So we will have the 10 read CSVs. So when it reads them, I'll get some item, will perform this series max chunk. So I'll get the maximum on that chunk, we'll report that. And then after it gets the maximum of all those chunks, it will send it, and then we'll get the aggregation and we'll get the maximum at the end. All right. So up to now, everything has been lazily executed. If we want to see the result, we need to hit compute. So when we hit compute, let's see what we get. So now things are happening. Boom. There we go. In 2 seconds, my machine list, we got this. I'm not sure how long this takes in pandas, but we'll have to go through a for loop, and then it'll probably take up maybe a minute or so. So again, here we got my 8 threads. You see this operation, the get item here. And over here, you see the series max chunk happen. When you see something red on the dashboard, this is like a transfer. So it's more of a communication kind of thing. You see probably now that we have this workers memory that now is like 400 megabytes over here. If you are in Binder, you will see a little bit less. And total, we have about 1.8 gigs of data in RAM over there. So another operation or pandas-like operation that we can do is, for example, let's try to, oh, there's a typo here. No, can. So there we go. Let's say the total of non-cancel flights taken. So notice that there is a column on our data frame called cancel. So if we want to say the no cancel in pandas, what you do is this sort of operation. The curly thing is like when we are like saying no this. So we want the non-cancel. Then we want to sum them. As you know, if you notice, or if you check the data, we can take a look at head back in here, cancel. Let's look for that column and see if we can see it. It's a Boolean. So it's a false, 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 or true, depending on if it was or not canceled. So we can sum that. We can sum them and then compute. And then we see how many are. So let's try that. There we go. So we just did bunch of cancel things. In this case, something that we can check is what is the length of the data frame. So in this case, I have around 2.6 million. 2.6 million rows. If you're in Binder, you will have less data, but we're going over all this data kind of like a little bit fast. So other operations that you can do, and they're fairly common, and you might wonder if you can do, is like group by like operations. So that can be filtered, and you can check, for example, in this case, if we want to know the total of no cancel flights taken by airport. So you know that we want the non-cancel ones. So this is a type of like filter. Then we'll group by origin. And then out of all those origin ones, you will do a count and then compute. So this is a little bit of a long syntax, but the only difference with the pandas operation, it will be that we're adding this compute. So let's see how this looks like. We're seeing stuff with some transfer here. We got this unmanaged and managed memory. As I say, don't worry about now what that means. But if you're interested in knowing a little bit more about that, there's a great blog post that was recently released from Coiled that explains a little bit more about that. So I'll drop the link later on the chat. Now, one example you can do it as an exercise so we can see it together here is what is the average departure delay from each airport. So again, more pandas-like computations, just add the compute. So we know that we can group by origin, which are all the different airports, and then take the mean of the departure delay and then compute. So click on that. You see more things happening, that we have more different tasks. So we have the read Csvs here, And as you notice, so far we've been doing a lot of read CSVs that we could probably do it only just one, or less time if we will compute all these things sort of together. We'll see a little bit of how to deal with things like that in a second. So right now we're reading CSV. We have different colors for different tasks. So the group by chunk. Then we have this group by some chunk. You notice that we have some white space. So in the dashboard, when you see a lot of white space, that means that the workers are not doing things. They're waiting to do stuff. So in general, if you see a lot of white space, that's usually not a good thing. In this case, they're like milliseconds. That's something that the dashboard is useful for. You want to keep an eye for that. If you see a lot of red, that's a lot of communication. Probably that might mean that either your chunks are super small, or that maybe Dask is not the best use. You want to use all that information to evaluate and then see how to let's say redesign your computations. So another one will be what day of the week has the worst average departure delay. We can just compute that and see more, and you see more tasks over there. Now they're going fast. In the future, we're going to explore a little bit more of what's happening in that progress bar. So quick performance tip to share is that what we were mentioning before. We have a bunch of like non-cancel. So we're dealing a lot with this kind of filter in these computations. So if we were to perform, let's say, the mean and the standard deviation of the non-cancel things separately, that will take a certain amount of time. So let's see what happened when we do that. So if we take this time, we are going to compute the mean, and we're going to compute the standard deviation of the departure delay of the non-cancel flights. So we'll go there, and we'll see these two computations happening. That took about 3 seconds. Now, you might notice that we can compute these two, the mean and the standard deviation, together, right? Because they're both using this. So let's see if we can just create a test graph that actually looks a little bit better. So when we do this, we actually can see that now things takes a little bit less time. And when we're using Dask compute here, it takes roughly half. It depends sometimes, but in general, it takes less time. And this is because the task graphs for both computations over here are being merged. And when we're calling like Dask compute, we have the read CSV part that is shared. So we don't need to compute read CSV twice. So if we take a look at the graph, but it's a little bit hard to see here, but you will see down here that the read CSVs are being shared. I believe that is down here. I can see properly, but my guess will be, let's see. Yeah, if we make it bigger, you will see that down there, those read CSVs are shared. So that's good. All right, so far we learned about Dask Delayed. We learned about the different schedulers, how to go from pandas to Dask. So let's see how can we do a little bit of machine learning using Dask and hopefully run things faster. So I'm going to close this client now, and then we're going to go to our last lesson. We have here. Right, let's do some machine learning. So this notebook is based on gray material that has already been designed by the Dask community. So most of what is here you will find in different Dask tutorials that have been taught, but I just shrink down a little bit of that material so with the idea of showing you what we can do. So as we talked before, there are two types or overall different types of scaling kind of problems. So you have things that are going to be either CPU bound, so problems where data fits in RAM, but training takes too long, and then you just need more computation capacity to be able to perform it faster. So those things are what we call usually CPU bound problems. And then we have memory bound problems where your data is larger than RAM and sampling isn't an option. So then you probably need a bigger amount of memory, or you could actually use Dask to handle that. So as we mentioned before, if your things fit in RAM and you're not compute bounded, you just want to live in Scikit-Learn, pandas, NumPy, you necessarily need to, you won't need to go to Dask. But then everywhere else, if you're compute bounded or memory bounded, Dask is a fair game. And there has been great integrations between Scikit-Learn, JobLab, and Dask to be able to actually use Dask as a backend. So then pretty much your Scikit-Learn workflow can just scale with adding few lines of code. So super quick, we're going to be doing some Scikit-Learn in five minutes. And then we are going to see how can we use Dask as a backend, how can we use JobLab, and then later on, we're going to see how to scale things and run on a cluster, like on a Coiled cluster, for example. If you are in Binder, running in Binder, I would suggest that for the second half of this notebook, you just follow along. The resources that we have in Binder are super limited, and these things are going to take a long time to run. So you don't want to follow behind, or you can make things smaller, try to play with the size of the data. But for now, super quick, some of you might be familiarized with Scikit-Learn, some of you might not. But in general, well, some kind of workflow that we do with Scikit-Learn is we load some data, we import a Scikit-Learn module, and then we choose our ML algorithm. We create an estimator for that algorithm, fit it with our data, and then inspect some learn attributes and check the accuracy of our model. So I just summarize super simple what you will do overall when you're playing with Scikit-Learn. Of course, this is like an oversimplification. Please, if you are into data science, machine learning, just don't get offended. I didn't mean to simplify things. But for the purposes of this tutorial, this is what we're going to be doing. We're not going to get super fancy with the things that we're going to use. So first, we will instantiate an estimator, then we'll fit, then we'll get some information out of it. So to get started, for now, we're going to do a little bit of just Scikit-Learn. So we'll generate some data. We're going to do some data. We're going to generate some data that we're going to use for classification. So here, still on Scikit-Learn land, and we'll have X is a sample matrix or a design matrix. And the size of X will be typically the amount of samples that we have times the features. And which means like the samples are represented by rows. So you can think this of as a matrix. And then the features are represented by columns. And a feature is an attribute. Let's imagine that we can say we have every entry is a person, and we have like 10,000 people. And then we have 4 pieces of data on each person that will be, I don't know, height, age, color of hair, and years. Well, age and years are the same, something different. Color of hair. If I didn't say that, I'm getting limited with my options. But imagine 4 different attributes of a person. And then Y will be a target value, which are usually real numbers for regressions and or integers for classifications. And that is what we will be trying to sort of predict. If we are in unsupervised models, then Y does not need to be specified. But in general, things for this case will look like this. So we got 8. We just got the first 8 entries. So there will be the first 8 people. And then we have 4 columns. So that 1, 2, 3, 4. And then we'll take a look at Y. And this has zeros and ones, so that this could be, does this person like ice cream? Yes, no, yes, no, yes, no. Something like that could be this entry. So let's try to fit a support vector classifier. We're not going to get into much of the explanation of what the support vector classifier is. If you want, you can check the documentation. But here, just do some dot. We get the support vectors, and we can score our estimator. And there are multiple ways of scoring and getting like there are different approaches about this. We're not going to get into that right now, but for now, we just see that we have a number and we're happy. Now, if you want to explore more parameters and play around with different kind of estimators and see which ones could be better or not, and then try to get the different scores, what we will do is a grid search. And we can do that with Scikit-Learn. So we will go over all these different combinations of the parameter C and the kernel, and then see which one of this one give us a better fit. So if we time this in Scikit-Learn, this should take a couple seconds. It's not a big problem. So far, we're not doing anything in parallel. So bear with me. It says a super quick intro to Scikit-Learn. And it took 14 seconds. Now from here, we can get which one are the best params. So these are the best params for my model, and this is how it's scored. So now this problem is a kind of problem that if I keep adding parameters in here, I'm running like just the same thing with different parameters. So this is what we call the compute bound problem. So let's see how can we use joblib, which is a tool that it's a great tool, and it's like a lightweight pipeline in Python. So it will give us parallelism in our lab. So here we'll have some sort of graph where we are going to be doing this operation or the different combinations of these parameters in parallel, because we don't need to run them all together. So in Scikit-Learn, if you worked with Scikit-Learn before, you might have seen this keyword argument. It's called njobs. And if you usually put it to -1, it tries to use run as many tasks as it can in parallel. So if we try to do that just by adding this -1, we'll try to run things in parallel. And so far, we're not using any Dask yet. We'll see now how can we use Dask and the Dask backend to compute these things. But for now, if you notice, here we're running around 7 seconds, while before it was taking 14 seconds by only adding this njobs equals -1. So now let's take a look at how can we do this with Dask. So we will create a client. So then we'll see our beautiful dashboard we'll have over there. And now let's just run way more of these ones. So we'll have all these different parameters and all these different combinations, and let's see we can run them with Dask. So the way we'll do that, so far, similar things. We'll just import joblib, and we will create this context manager that what it's telling us is run joblib using the Dask backend. We'll pass the data, which is X and Y, and then do the grid search fit using the Dask backend. So let's see what happens now. So we're going to be running way more operations. So let's see how long this takes. In the meantime, something good to notice here, you might see these tasks are 6 tasks, and they're all like it's a full color. So this means that these tasks have been computed and have been released. So they were in memory and they have been released. The gray back here, it says these are the amount of tasks that are ready to be executed. So there we go. We got it on 32 seconds. So that's great. I mean, in 32 seconds, we just got 36 candidates. And then because we did like a cross-validation of 2, then we got 72 different fits. So now, ideally, we'll have more options, and then we'll see what are the best parameters. And then now we got this, that the best parameters are C equal 10, this kernel RBF, the shrinking through, and we get a score of 0.908. That's great. So other problem that you can have is what is called a memory bound problem. So now we're not limited by the computations, but by the memory that we have. So one problem, this is a very common problem. And ideally, what you will do is use Dask-ML, which has estimators that work well with Dask arrays and Dask DataFrames, and that might be larger than your machine runs. So let's see an example of that. And then let's see how can we deal with this. So for now, I'm going to create some data with blobs. So here we have some centroids, and I'm creating some data here. These are sample things and nothing too fancy. And from this, guys, noted that this is a small data set that will be a template for our large random data set. And we will use Dask Delay to adapt these blobs. Oops. And so the actual data set is being generated on the workers. So if you're not in Binder and your machine has more than 10 gigabytes, more than 16 gigabytes of data, you could actually run the following code with 200,000 samples, and it will take about 10 minutes on your laptop. Right now, I'm not going to run this computation with 200,000, and this computation actually won't be a memory bounded one, but I just want to show you like how the computation looks like. But this can be performed with 200,000 on my laptop in about 10 minutes. So here, let's just do this a little bit smaller so we see how it looks like. So I'm creating here, this is a 2.2 gigabytes array, and these are the chunks. When we run with 200,000, this is close to 16 gigs of memory, which means that my memory will be like in trouble. So, but it still be able to run. So let's see what happened on the dashboard when we run this. So now we will import k-means from Dask-ML. So we'll do that. I'm seeing like some things from the kernel before. So we run this. Then we get our model. So we'll use this, not doing much of here, just getting our model. Let's try to fit it and see how long it takes. So it's doing things. So one thing that you see now in the dashboard is that you have different colors. So you have the solid gray. Those are the tasks that are ready to be executed, but are not being executed yet because just we don't have enough resources. Then you see that there is a solid a solid piece of rectangle there in the progress bar. Those are the tasks that are completed, but are still sitting in memory. And when it gets transparent, so you will see that over here in the sum, or in the green is more clear. In the amin or in the pathing, you'll see that now those are transparent. Like in the sum partial, you see there is a dark purple and a lighter purple. The lighter purple means that those tasks are completed, that were in memory, but now they are released. So we have a lot of information here. And you see it, all this on the task streams are individual tasks being computed as we go. And I'm seeing like, yeah, we have like about, in the cluster, like about 3 gigabytes of data. So this is getting close, probably will finish soon. But it takes a little bit of time. And it's a problem that is still, in this case, is not necessarily memory bounded because I'm not doing it, so I can show you, but you could run things that are much, much bigger. It'll take just 10 minutes. So now we're close to finishing. And you see, there we go. It took 1 minute and 52 seconds. So you can see the labels now, and we got the labels. And now I'm going to close the client, and I will show you how you can run this problem much faster using a cluster on Coiled. And if you are on Binder, you won't be able to do this. There are ways of connecting to the cluster from Binder, but currently I wouldn't suggest to do so right now for the purpose of this tutorial. But one thing that I want to show you is if you already have a Coiled account and you created an account, you get some free credits, so anyone can give this a try. You will do import Coiled, and you already will have Coiled installed if you install the following the instructions to install things locally. And then we'll actually, now we're not going to see, I'm not going to show you this custom. I want you to see something different. And then I'm going to create a cluster using a software environment that I already have set up for this. You could actually use the same software environment. So I'm going to request n workers. And for that, I want to show you how would that look on the Coiled side. So let's go to profile. If you already created an account, you will have to log in by following the setup thing. So I'm actually going to show this over here. So now these are some clusters that I was playing around earlier today, but I'm going to request a cluster. This will take a few minutes, probably 3 to 4 minutes. And you will see this, that this has the spending status, and we are requesting a cluster here. If you're doing this for the first time, it will ask you to fill in a token, and it will give you a link on where you will find the token. And you have some free credits to try. This is not a super crazy computation. So we'll now be able to, from my laptop or from my machine, be able to run things remotely on a cluster on Coiled. So that's kind of cool to me. I think being able to run things from my laptop, connecting to a cluster, have more resources than my laptop. That is kind of great. So you see now that this is running. It's still not quite there yet. I don't have my workers. So these are our machines that we are requesting. So these are Coiled workers, right? So I'm requesting like kind of 10 different computers, and we'll see how our cluster looks like once I connect to it. So we're still waiting a little bit here. Here in the dashboard, you could access the logs. You have a quick install and quick start here. So if you want to follow along, eventually there's a good amount of information on how to connect and run things. You could follow the quick start. There's great documentation by our software engineers. So it's taking a few minutes, hoping that this will be here soon. Now, in the meantime, what we'll see is like now, by being able to request this like bigger machines, then my computations should take less time. It also depends on the kind of computation, but then also I should be able to run bigger computations because I have way more resources. So it's taking up a little bit, but so far, if you want to start and spawning up your cluster, in the material you have, there we go, we got a cluster. We're almost done. So we're getting our workers, and then now the way that we connect it is we just connect the client now to our own cluster. So if we click on there, you'll see that now we get a different link. And here, now you have a different dashboard. So I'm going to show you the dashboard. Oops, over here. So now this looks a little bit different, right? Like we have 1, 2, 3, 4, up to 10 workers. So now the dashboard looks the same, but now we have more resources. And if I take a look, well, this is 10 workers, so probably I missed one. Let's just set that. There we go, 10 workers, and we have 75 gigs of memory, 20 threads. So it looks a little bit of a bigger machine. So let's do the same computation that before, but now instead of running like doing 30,000 samples, then we will get 200 samples. So let's kick this in. Now we're going to persist the data on the cluster, and then we'll do the same operations. Here we go. So yes, the others. We will be adding explanation with the colorings and stuff on the next iteration of the tutorial. I realized that that is very useful, so we will actually add those things. Thank you for the feedback. So you see now things are happening here. There's a little bit more red, so it's more transferring, and we're getting our computations going. We're seeing the tasks are processing, and there's some kind of like a stop time. But ideally, this computation will run in 1 minute or 2 minutes, hopefully. But now instead of having just 60,000 samples, we have like 3 to 4 times more with 200,000. As we see how this computations goes, then thank you all for being here today. I know it took a little bit longer than what we expected. Please send us any feedback that you would like to see, things that we could improve. And then if you have any more questions for me, I know that Ian has been replying most of the questions in the chat. Please feel free to post them. But here we go. As you notice, we have like 1 minute and 39 seconds, which took less time than if we checked before. We had over here, oops, where is it? When we ran this computation, it took 1 minute, 52 seconds. And now in Coiled, we run 3 to 4 times more the amount of data. Actually 30, so actually more than 6 times, 6 or 7 times the data. And then now we got it in 1 minute and 39 seconds. So there are plenty of more resources in here. Thank you all for staying with me. And if you want to learn more, like feel free to give us again a lot of feedback, and then we'll happily write some more material for you. I'll stay a little bit more if you have any questions, and if you don't, I will leave you to this. There are way more resources on the links. Then if you're interested in having a more intense Dask training and Dask tutorial, Coiled currently offers Dask trainings, and I believe that we can post the link in the description or in the chat right now. And then there are usually early birds and then some bonus and discounts that you can get for that. Those are usually 2 days tutorials. So we will be happy to have you there and register. So I'm going to drop the link over there. There are also plenty more material on the Dask community. Please feel free to join. We're always happy to have you. If you are having any bugs or issues, then there's always the issue tracker on GitHub. So please let us know, how can we help you? How can we help you in your journey with Coiled and or Dask or anything that you want to try? And that's all for me. I hope you enjoyed this. Thank you very much. And hopefully we'll see you soon. We'll probably send out some form or something to get any more feedback than we can do. All right, see you all. I'll be closing this stream now, unless you have any last minute questions. But again, thank you for joining us, and we really appreciate your time with us. Goodbye.